Who would like to ask a question?
I have two questions.
Okay.
Well, they're both with the pre-lab for the quantitative analysis of a pure compound pre-lab assignment.
Okay, hang on just a second. Something's bothering me on my screen. There we go. And do I need to open up the pre-lab, or can you describe the questions to us?
It's questions 5 and 6.
Okay, so what is question 5?
5 is calculate the mass of calcium chloride needed for a 3 times excess for 0.7 grams of sodium carbonate and 0.7 grams of potassium carbonate.
Okay, so I'm going to do this for sodium carbonate, and I'm going to let you do it for potassium carbonate. So there's the reaction. And we want a 3 times excess, and here we're going to start with 0.7 grams. Does that sound right?
Yep.
Okay. So we're just going to do this. This is rounded off. You can do better than that, but it's about 106, okay?
Right.
This comes from the balanced reaction of 1 to 1.
Right.
And then let me look up something real quick. Now, this is rounded off, mind you. You can do better. Now, if we estimate, you can see that it's going to be around 0.7 grams, okay? Okay, is this number in excess, or is it the amount that you need?
It's excess.
Really?
Oh, wait.
Isn't this the amount you need?
Oh, yes. No, it is, yes.
So to get 3 times, you just do 3 times which is 2.1 grams, thereabouts, right?
Oh. Oh, that's all you do?
That's all you do to get a 3 times excess.
Oh.
Now, clearly, you only have about 3 grams of this stuff. If you use that much, will you be able to do this reaction with sodium carbonate and potassium carbonate and have the excess? You're using 2.1 grams for one reaction.
Right.
That means you'll only have 0.9 grams left over for the next reaction.
Oh.
Do you think that's going to be a 3-fold excess?
I think so.
Well, let's think about it. This requires 2.1 grams. If I do this, the answer is probably going to be close to 2 grams also. So if you use 2 grams for this reaction and 2 grams for this reaction, do you have enough?
No.
No. So maybe you try 0.5 and see if that works.
Oh, all right.
What would this answer be if we had 0.5?
It'd be 1.5.
Yeah, it would be like 1.5.
Yeah.
And this would end up being about 1.5. So would that be enough?
Yes, that would be enough.
So to calculate a 3 times excess, you calculate the amount you need, then calculate the excess.
Oh,
That's it.
oh, it's not bad.
Yeah. How about number 6? What does that ask?
Number 6 is asking, look up the water solubilities of calcium chloride, sodium carbonate, and potassium carbonate. Do this to determine if 10 milliliters of water is enough water to thoroughly dissolve each of these separately.
So what did you found for calcium chloride?
Well, I tried looking it up, but I didn't really know what I was looking for.
Well, let me show you how you might do this, okay? So I'm switching my share, and I'm going to go to water solubility, CaCl2. And these search engines are so forgiving that if I even type this in like that, which is not the right formula, it'll probably give me a correct place to go. So here's calcium chloride, Wikipedia. I'm going to go here. And if you look to the right, do you see the list of properties? Density, melting point, are you with me? And then you see the solubility of water. So 20 degrees Celsius is approximately room temp. So this says that 74 grams dissolves in 100 milliliters. So let's calculate how much dissolves in 10 milliliters. So I'm going to change my share. Whoops, I opened a poll question. Change my share. So it's 74.5 grams per 100 milliliters at 20 degrees Celsius, which is roughly room temperature. And you're going to be doing the experiment at room temp. So we're going to take our 10 mils, multiply by 74.5 grams over 100 mils. And we find out that 7.45 grams will dissolve in 10 mils. So do you plan on dissolving more than 7.45 grams?
Muted. No.
We just did the calculation about how much do you expect to dissolve?
Oh, about 3 grams.
No,
No, wait.
1.5 grams.
1.5, sorry. Yes, so no, you're not expecting to do 7.45.
So is our 10 mils going to be enough to dissolve that?
Yeah.
Yeah. So the whole point is that this reaction is not going to happen if things aren't dissolved. So if you used 1 mil, it wouldn't work. But 10 mils should. Does that help at all?
Yes. No, that does help.
Okay, good. All right, does anyone else have a question?
Oh, I have a question on 9 and 10 on the pre-lab.
Okay, On, go ahead.
Yeah, so 9 is asking what is this advantage of forming insoluble carbonate instead of insoluble sulfate?
Okay, so disadvantage of calcium carbonate as the solid, right? So I'm going to do a share here. And I'm going to go back to the internet. Only here, I'm going to go to our website, our Canvas site. And I'm going to go to the lab. Okay, so here's the lab notebook. Okay, so can you see the highlighted text?
Yeah.
Why don't you go ahead and read that?
Sulfate ion is used to this.
Oh, you don't need to read it out loud. That's
No,
fine.
I mean, yeah, I know. I just read it right now.
So why is sulfate ion soluble a good thing? Sulfate ion is used in this instance because most sulfates are soluble, whereas barium sulfate is not. And the answer lies in the fact that we want to collect the barium sulfate, right? What if
Yeah.
sulfate ion was not very soluble and it would precipitate with other ions? Would that be helpful to us? And the answer is no, because here the deal is when we collect the precipitate, it's supposed to be all one thing. And if it's all one thing, we can figure out how many moles of it. But if it were two things, how would you figure out how many moles of sulfate you have? Because if you had two things, you wouldn't know how much of it was one and how much was the other.
Okay, so
So what's
I
the
think I kind of got the idea.
disadvantage of the carbonate ion?
Um,
What's its solubility rule?
so so the carbonate ion is it will be insolute.
Right, it's insoluble.
Yeah.
So that means if you have other ions in there, other cations, they will make a solid with the carbonate, and the solid that you're collecting is not pure calcium carbonate. So you wouldn't be able to calculate how much carbonate you have. So that's the disadvantage to this reaction, is that it's not very specific. But the reason it works for us is because we're using a pure substance. All right?
Yeah.
Okay. Who's next?
Oh, and then I have a number 9 too.
Okay.
They're asking like in a barium sulfate lab, the sulfuric acid is added and introducing more sulfate ion, which help barium sulfate precipitate.
Right.
And asking why adding acids to carbonate reaction is very bad idea. I think it's kind of the same reason for the.
No.
Carbonate.
Here, this is a carbonate, and this is an acid. What do these form? So what happens here is your carbonate gets dissolved, and it gets turned into CO2, and then you get calcium sulfate instead. And this stuff is soluble.
Can you share the lab?
Oh, I'm sorry. I'm sharing the wrong thing. Thank you for letting me know.
Yeah. Yeah. Oh.
So this is a gas.
Oh, okay,
This is
okay.
soluble.
Yeah.
And this is a liquid. This
So we can.
this solid dissolves, and you don't collect anything in your paper.
Yeah. It's hard to see. Yep.
So this is why we don't want to add acid.
Yeah.
Any type of acid, including sulfuric acid.
Mm-hmm. Okay. Thank you. Yep.
You're welcome. All right. Harry, Jackie, any questions?
I actually had a question on number 7 of the pre-lab.
Okay, go ahead and can you read that to me?
Yeah, it says why is the calcium chloride solution added to the sodium carbonate solution instead of the other way around?
Okay, so here's your sodium carbonate solution. Here's your calcium chloride solution, right? If I take this one and add it to this one, I'm going to get sodium carbonate and calcium chloride, right? And we want to make sure every one of these reacts. Are you with me here, Jackie?
Yeah.
Okay, so when you pour from this test tube into this test tube, is there ever any stuff left behind?
Yes.
Little droplets. What's inside that droplet? Sodium ions and carbonate ions. And you're supposed to react every single one of these. And you left some behind. You abandoned them.
Oh,
I'm
okay.
trying to make you feel like a bad person. You've abandoned those carbonates in this test tube. Now,
Right.
what if we do it the other way? What are we leaving behind here in the calcium chloride solution? We're leaving behind calciums and chlorides. Now, we want this to be in excess, and it's in 3 times excess, right? So if you leave behind a few calciums and a few chlorides, do you care since they're in excess?
No.
No, because what you transferred is more than enough to react with this. So this means all of your precipitate will be in here, and you don't need to worry about some of it not forming because you never reacted it.
Oh, okay. That makes sense. Thank you.
Okay. So it's just a matter of trying to make sure you react every carbonate ion. Now you could do this, Jackie, but what would you have to do to make sure all of these get into there?
Could you rinse it with water?
Right. Now, what would be the downside of rinsing this with water and putting it in there? The answer is you have more to filter.
Oh, okay.
Did this take a little bit of time to filter or a lot of bit of time?
I think it kind of took a while to filter out.
Yeah, it took a while. And then the rinses took a while to filter out, right?
Yeah.
So if you were to add more water, you would increase the time you needed for the experiment.
Okay.
So you always want to think about these things when you're doing an experiment. How can I make it work the best, including how can I use my time most wisely? So that question was addressed to that. Okay?
Yeah.
All right, good. So these questions are supposed to make you think. Are they making you guys think? You may not always get the answer, and that's why we have these Q&A times. I am willing to tell you the answer if you've thought about it a while. All right, who's next? Okay, you guys know the drill. Here's a question from the book. I'm not sure, am I sharing my screen with you so that you can see the question?
Yeah.
Okay, so here, I'm going to go through how to do this problem. And once you are good with that, if you're good with my explanation, you're going to give me a thumbs up, and then we'll move on. If you're not good with my explanation, I expect you to unmute yourself and ask a question. Are we good? We're good with that? If you're not good with that, you're supposed to unmute and ask me a question. Are we good with this?
I'm good.
Do you know how to choose thumbs up? Okay. So what volume of 0.12 molar sodium hydroxide in milliliters contains 25 grams of sodium hydroxide? So one of the things you want to do is write that out as a ratio. So when you write that out, you see that you can go from liters of solutions to moles of solutions, right? Liters of solution to moles of solution. Now they want the answer in milliliters, so I kind of have the feeling that to get my answer in milliliters, I'm going to have to first get my answer in liters and then convert to milliliters. Here, since I have this conversion between liters and moles, I think that if I have moles of sodium hydroxide, I can calculate the liters of solution. And lastly, I have the feeling that if I have the grams of sodium hydroxide, I can then figure out the moles of sodium hydroxide. So you see my pathway to solving this when I actually started with what I wanted, and I figured out, well, how do I get to here in one step? And it seemed to me that since this was in liters, I'd better go from liters to here. That just made sense. Okay. So now let's take a look at the process. Now the molar mass of sodium hydroxide is 22.99 plus 16.00 plus 1.01, which puts us at 40.00. And so now I'm going to use this concentration, but if I use it the way written, I'll have moles times moles, so I'm not going to like that. I'm going to put the 0.123 moles on the bottom and 1 mole on top. Oh, excuse me, 1 liter. Okay, so here the moles cancel, the grams cancel, and lastly, we want to remember that for 1 liter of solution, there's 1,000 milliliters of solution. And when we estimate the answer, how can we estimate the answer here? Well, the way I would probably do it is 40 goes into 100, 25 times? 25 times 25 is 625. 625 divided by 0.123 has got to be like 6,000 or something like that. And actually, I think I did this wrong. No, I think I'm okay. So let's see what we get. $25 times 1,000 divided by 40 divided by 0.123, and we get 5,081. We are allowed 3 significant figures, so we have to do 5.08 times 10 to the third milliliters of solution. Are you okay with the solution and the explanation? Are you okay with this, On? You got to select the thumbs up. Okay, then we're going to move on. I'll give you guys a chance to read this. So I'm going to take this and I'm going to go ahead and write it like this. So this uppercase M always means moles of the solute per 1 liter of the solution, 1 liter exactly. We want to get the mass of solute, which is sodium phosphate. Now, given that this is molarity, I kind of have the feeling that if I have the moles, I can probably calculate the grams. And that means that if I have the liters of solution, I can calculate the moles. And here I have 125 milliliters. So I think I'm going to go from 125 milliliters to liters, liters to moles, and moles to grams. Now, what is the molar mass of sodium phosphate? 3 times 22.99. I have to look up the molar mass of phosphorus. I don't know it. 30.97. And then plus 64 for 4 oxygens. And if I estimate the answer, 31 plus 64 is 95. 3 times this is going to be, what is that, 69? So 69 plus 95 is going to be 174. Oh, I was off by 10. It's 164. I see that now because 90 plus 60 is 150. So 163.94. Now you don't need to wait for me to write out the solution. If you find that you're getting a little bored, start writing this out and then see what I do compared to what you do. Because this is what I'm looking for on the test. And here I should have sodium phosphate. Okay, so let's make sure everything cancels as it should. And we're left with grams of sodium phosphate. And if we estimate the answer, this will go into this about 6 times. 6 will go into that about 20 times. And 20 times this ends up being 2 times 10 to the minus 3. And I get looks like 3 significant figures. 2.10 times 10 to the minus 3 grams of sodium phosphate. Are we good? Okay, then we're going to move on. So I'll give you a moment to read this. Okay, so we're going to do this one a little bit differently now. I'm going to let you solve it. Give me the thumbs up when you're done. So the first thing I would do is write this out. And then here, I want liters of solution, which means I'd better figure out how many moles of KMnO4, which means I'd probably better start with grams of KMnO4. Now this problem is a little tricky, and then it says 3.22 grams of solute. The KMnO4 is the solute. That is the dissolved material. Let's see, 1 potassium is 39.10. 1 manganese is 54.94. And 4 oxygens is 64.00. Okay, so did anyone else get 163.14? For the molar mass? Okay, and then times. So when I estimate this, it's kind of hard to do.
Wait, for the molar mass, I got 158.
158.04.
158.04.
Oh, I thought this was a 9. Thank you. This is a 4. I thought it was a 9. So we should get an 8 here, and it's 158. Does that look good now?
I think it's 158.04.
04.
Yeah.
Oh, that's right. I don't carry a 1. So my addition is sucking. At any rate, so this will go into this about 0.02 times. This will go into this about 0.01 times. So the answer should be about 0.01, right? Let's see what we get. And we get 0.00989 liters of solution. 3 significant figures and 3 significant figures. Okay, so does that solution look okay? Okay, we'll move on then. Identify the ions that exist in each aqueous solution and specify the concentration of each ion. So for A, we have barium ion and chloride ion. So those are the ions that exist. Specify the concentration. So I'm going to take that and write it out as moles per liter. Now I'm going to multiply by 1 mole of barium ion per 1 mole of barium chloride. Because for every 1 mole of this, there's 1 mole of ion. The formula tells me so. So when I have moles per liter, I can write molarity barium ion, and I can see that this ends up being 0.12. So how would the calculation for chloride look? It'd look like this. Okay, any questions about the solution for A? Or are we good? If we're good, give me a thumbs up. Okay, so I'd like you to do C, and I'd like you to write out the solution just like we did for A. So I'm going to clear all. I'm going to pause the recording. You give me a thumbs up when you're ready to look at my solution. Okay, so again, to figure out the ions of this formula, because we have K at the front, we know that that's a cation, and we know that each one of these has a +1 charge. And once we've identified the cation, everything else must be the anion. There's only one because there's no parentheses. And then because this is a -2 charge for the 2, this has to be a -2 charge for one of these, and so it's got a -2 charge. So we would start off with 0.500 moles of K2Cr2O7 per 1 liter of solution. We would multiply by 2 moles of potassium per 1 mole of K2Cr2O7, and we would end up with 1.00 molar potassium. And for this is called dichromate. We would do it in a similar fashion, only it would be 1 mole of dichromate per 1 liter of, or to 1 mole of potassium dichromate. Okay, if you're good with that, give me a thumbs up. Okay, we're going to move on. I'll let you do B on your own. So here's one question. This is about preparing solutions. I'll let you read it. All right, now here, what mass of oxalic acid? So I'm going to say grams of H2C2O4. That's what we want. Now, I have the feeling that since we're doing these problems, I probably will need the moles of oxalic acid here, which means that here I would probably like to know what? The liters of oxalic acid, right? Or liters of solution, I should say. And here, I would imagine I'm going to start with milliliters of solution. Sure enough, we've got that 250. This little dot is tricky. You don't want to miss that. All right. In addition, what does this 0.15 mean? 0.15 moles of oxalic acid per 1 liter of solution. So let's put it all together. For oxalic acid, we have 2.02 for the hydrogens, 24.02 for the carbons, and 64.00 for the oxygens. Okay, when I estimate the answer, 250 goes into this 4 times. I'm going to do 1.15 times 70 because I know 0.1 times 70 is 0.7, or excuse me, 7. I know 0.2 times 70 is 14. And since 0.15 is between 0.1 and 0.2, my answer should be halfway between 7 and 14. And halfway between 7 and 14 is roughly what? 10, 11? So 10 or 11 divided by 4 gives me 2.5, roughly, for an answer. And we don't get 2.5, we get 2.63. So on an exam, this is the work I expect to see. You don't need to map it out. You don't need to write the molarity out because I see it right there. But I do expect to see a nice solution like this all written in a row like that. So is everyone good with this solution? If you are, give me a thumbs up. Okay, so now I have a question for you. Are you finding that doing problems like this helps you with the exam and writing out the solutions? If it does, give me a thumbs up. If not, give me a thumbs down. That was a pretty quick thumbs up. Okay. Maybe one of you in the Q&A part where you're supposed to post something, you might want to post, when we do problem solving, it really helps me with the exam. And maybe other students will start watching these videos. Okay, let's take a look here. Oops, I skipped ahead. There's another problem here. So I'm going to put this up here like this. So I'll give you a moment to read it. Okay, now for a problem like this, normally when you see the word diluted, you're going to use this formula here, where C is concentration and V is volume. So this is basically the initial, and this is the final, which is also called the dilution. Dilution just means the diluted solution. And here you can see what is the molar concentration in the diluted solution. We want C2. So I can rearrange this formula and get C2 is equal to C1V1 over V2. In this case, C1 is 0.0250 molar copper 2 sulfate. V1 is 4.00 milliliters of solution. V2 is 10.0 milliliters of solution. And you'll notice the way this is worded, it says it's diluted to 10 mils. That means your final volume is 10 mils. So the nice thing about problems like this is that even though this is milliliters and we think we need liters because this is moles per liter, and even though we would normally write this out as moles per liter, we'll find out that for these dilution calculations, we don't have to. So let me show you how it works. There's C1. There's V1. And I should really write solution here. There's V2. And you can see that the milliliters of solution cancel, which means our answer is going to be M, or molarity, of copper sulfate. So we can see that 4 over 10 is about half. So about half of this is 0.012. It should be a little less than that because this isn't quite 1/2. So let's see what we get. And we'll get 0.01 is what my calculator says. But what should I write down? Well, I know it should have 3 significant figures. So there are zeros here that I should write down. And this is what I would expect to see for your answer. Now, I want to tell you an additional thing here, okay? This would get you full credit, but if you mangled this answer and didn't get 0.100, you wouldn't get full credit. And if you put these numbers in here wrong, you wouldn't get full credit. If you really didn't know what the heck to do, but you wrote just that, I'd probably give you 1 point just because you know or this. If you wrote this or this, I'd give you a point just because you know something. And that would be partial credit. I think if you look at your test, you'll see that it was a rare situation where you would get 0 points for an answer, but instead, I would award you partial credit for what I thought was stuff that was worth giving you credit for. So, first question, are you okay with this solution? Okay, next question. So are you okay understanding that the more good information you put down, the more opportunity I would have to give you partial credit on an exam? So do you understand that if you put stuff like this down, even though you don't need it for the solution, that you could get partial credit for this even if you have nothing else? Okay. All right. Next one. Calculating and using pH. So saturated solution of milk of magnesia has a pH of 10.5. What is the hydronium concentration of the solution? For pH, there are two formulas you need to know. One is that pH is negative log of the hydronium ion concentration. And the same equation written differently is this. These are the same equations written differently. Just like this equation is the same as this equation. They're just written differently, okay? All right. So for this problem, it has a pH of 10.5. What is the hydronium ion concentration? We're going to use this equation. Now, if you leave an answer like this, I will give you hardly any credit at all. In chemistry, we don't like answers like this, especially where the power is not a whole number. So this is the only time that I like to use the caret button on my calculator. This button right here, the caret button. So you put 10 caret negative 10.5 and then enter. And it's hard to tell, but this says 3.1622 times 10 to the minus 11. 3.1622 and some more numbers. And that is a molarity concentration. Now, what are we supposed to report here? So what's the rule for significant figures? You look at these two numbers here. This has 3 significant figures, so this gets 3 digits after the decimal. Okay, so is the solution acidic or basic? You need to memorize the scale. For the pH, if it's less than 7, it's acidic. If it's 7, it's neutral. And if it's greater than 7, it's called basic. So here the pH being 10.5 is greater than 7, so it's basic. Any questions here? Are we good? Okay. So here, what is the hydronium ion concentration of a solution of 1.2 times 10 to the minus 4 molar solution of HClO4? This one has a nuance to it. The nuance is this. This is called perchloric acid. It's a strong acid. So that means that when you put this into solution, every one of these hydrogens comes off and adds to water and makes the hydronium ion. So here you start off with 1.2 times 10 to the minus 4 molar, but it reacts with water. So if all of this reacts with water, what's its new concentration? 0. And if this concentration essentially starts at 0, but all of these react, what is its new concentration? 1.2 times 10 to the minus 4 molar. So to calculate the hydronium ion concentration, it's just that. So pH is equal to negative log of 1.2 times 10 to the minus 4 molar. Now notice here we have two significant figures. So actually, now that I think about it, I did it just the wrong way. I did this backwards. This has 1 digit after the decimal. So here we're only allowed 1 zig fig. That's the way it works. Clearly, I'm not good with the logarithm significant figures. Okay, so here this has 2 zig figs. So the pH, 2 zig figs. So the pH gets 2 places after the decimal. All right, so here on this calculator, what you're going to press is negative log 1.2 second EE negative 4, and then enter. And here, since this has 2 significant figures, I get 2 places after the decimal, so we get 3.92. Okay, so is this acidic or basic? I know it's not a question up here, but I'm asking anyways. Acidic or basic? The answer is acidic because it's less than 7. Okay. We're going to do this as the last problem. Then we'll do some stoichiometry problems on Wednesday. So here, this says complete the table. We don't really need to show the work. So I'm going to recreate the table. And I want you to go ahead and work this table out, get the answers, and then we'll compare each other's answers and see if we all got the same answers, okay? When you're done, give me a thumbs up and we'll compare answers. So give me a thumbs up when you're done with the table, and we'll compare tables. Guess I should pause this. Otherwise, you guys are going to be watching nothing. Okay, so when you fill in the table, we get 9.17, 5.66, and 1.60. These have two numbers after the decimal because there's two significant figures here. Here, because there are two numbers after the decimal, this only gets two significant figures. Because this is above 7, it's basic. Less than 7, acidic. Less than 7, acidic. And less than 7, acidic.